Hello everyone, Assalamu alaikum. Welcome back for another video in the series of VLSI systems. Now in this video we are going to dive into an essential topic in digital electronics, that is pass transistor circuits. If you're studying CMOS circuits or just want to learn about how transistors work in digital circuits, this video is for you. We'll go over the basics, examine truth tables, and explore an example circuit to see pass transistors in action. To begin, let's discuss what pass transistors are. Typically, in CMOS circuits, the goal is to connect the output to either the power supply or ground to define a digital logic level. Pass transistors take this concept a step further. Here, instead of only switching between power and ground, the output can connect to power, ground, or even one of the input signals. In this configuration, the MOSFET is termed as pass transistor, meaning it can allow current to pass through in either direction, depending on the inputs. Now let's take a closer look at how pass transistors function in a circuit. In an n-channel pass transistor circuit, there is something called a floating node represented in the truth table by the letter Z. This floating node indicates that the output doesn't connect to the defined high or low level logic. For example, if both the inputs A and B are set to 1, the output voltage at node X is defined by a minimum of 2 voltages minus the threshold voltage, that is VT. So if A and B are at 3.3 volts and the threshold voltage is zero point 0.6 volts, then the output voltage, that is Vx, will be 2.7 volts. This reduction in voltage can pose challenges, especially when cascading multiple pass transistor circuits, as it may lead to unintended drops in the output voltage. As a result, it is not recommended to connect the output of one pass transistor to the gate of the next pass transistor, as it will only degrade the output, and in turn, if it is connected to a long number of cascading stages, then the transistor might not even turn on. At its core, a transistor can act as a switch. In the context of pass transistors, this switching ability means that we can control the flow of signals within a circuit, connecting different nodes or even influencing the path of current. However, understanding how the floating nodes and voltage drop works is crucial to designing effective circuits with pass transistors. Now let's take a closer look at one of the interesting characteristics of MOSFETs when used as switches. That is why PMOS transistors pass a strong 1 and NMOS transistors pass a strong 0. This is a key concept to understand in pass transistor logic. In MOSFETs, we use two main types of transistors, PMOS and NMOS. Let's start with NMOS transistor. When it's used as a pass transistor, it has no problem pulling the output node down to strong 0 or ground level. This is because the NMOS connects the output directly to ground when it's conducting, creating a very low resistance path for current to flow. However, when we try to pass a high voltage, the NMOS will only bring the output up to a voltage just below the actual high voltage due to a threshold voltage drop, or what we call as VT. This means that the NMOS is better suited for passing 0 rather than a full 1. On the other hand, PMOS transistors work a bit differently. A PMOS transistor can connect the output directly to the power supply, which allows it to pass a full 1 or high voltage without a threshold drop. But when we try to pass 0, the PMOS transistor struggles because it can't pull the output fully down to the ground due to same threshold voltage effect. So in this case, the PMOS transistor passes a strong 1 but not a strong 0. So knowing which transistor type to use for passing specific logic levels helps us optimize the reliability and efficiency of the circuits, especially when we are dealing with cascading pass transistors in more complex designs. To solidify our understanding, let's go through a quick example of a pass transistor circuit. In this circuit, we observe that the transistor behaves as a switch, connecting the output to either a high or a low state depending on the input configuration. This example illustrates the behavior we have discussed, that is, loading nodes, reduced output voltage, and the unique switching properties that pass transistors offer. While pass transistors can simplify certain circuits, it's important to keep their limitations in mind. Let's try to figure out what the voltages at different points, that is A, B, C, D, E, F, and G, will be based on our understanding. But before that, let's consider the initial conditions that are given. So initial voltage on each node is 2.5 volts, and relevant transistor parameters are VDD is 5 volts, VTN is equal to 1 volt and VTP is 0.7 volts. So remember that for NMOS transistor, the for NMOS transistor, the turning on condition for this NMOS transistor is that the gate voltage should be greater than or equal to VTN. And for PMOS transistor, it is reverse, that is, it should be less than or equal to VTP. So let's try to implement this and understand and check our understanding. So for node A, the transistor that it is connected to is NMOS, so its turning on condition should be the gate voltage should be greater than VTN. As its turning on condition is 1 volts and the gate voltage is 5 volts, so the transistor is on, so it will pass whatever is at the input. In this case, the input has ground voltage, that is 0, so it will pass 0, a strong 0, towards A. So output node A should have 0 volts. Next, we turn our attention to node B. Node B is connected to the output of PMOS transistor, and in order to turn the PMOS transistor on, the gate voltage should be less than equal to VTP. In this case, the gate voltage is 0, which is less than VTP, so transistor will turn on and 0 will be passed through PMOS. But if you remember the theory, an NMOS transistor passes a strong 0 but a weak 1, that is a degraded one, whereas a PMOS transistor passes a strong 1 whereas a weak 0. So because we are passing a 0, so what will happen is that the VTP will be added to this input signal because its output will be degraded in this case. So the output will be 0 plus 0.7, which is 0.7 volts. The next node is C. C is connected to the output of an NMOS transistor. So again, the gate voltage should be greater than VTN. In this case, gate voltage is 5 volts. So the transistor will turn on and input will be passed to the output node C. In this case, this is almost equivalent to the logic 0. So the input will be passed without degrading to the output. So C will have 0.7 volts. The next node under observation is D, which is connected to the output of a CMOS inverter. As we know that in CMOS inverter, either pull-up network or pull-down network will turn on. So in this case, because input is at 0.7 volts, the turning on condition for a PMOS transistor is that it should be less than equal to 0.7 volts, and for NMOS transistor it should be greater than or equal to 1 volts because input is at 0.7 volts. So PMOS transistor will be turned on and NMOS will be turned off. So the output will have VDD, which is 5 volts in this case. So D will have 5 volts. The next node E is connected to NMOS pass transistor. So the turning on condition for NMOS transistor is that its gate voltage should be greater than VTN. In this case, the gate voltage is 5 volts, so it will be turned on, and the input is also connected to this 5 volts, that is the node D. So input is 5 volts, which is one logic, and as we know that NMOS transistor passes a weak one or a degraded one, so the output will be degraded in this case. By how much? By VTN. So the output will be Vin, which is 5 volts, minus VTN, which is 1 volts. So the output at node E will be 4 volts. The next node is F, which is the output of again an NMOS based pass transistor. Its gate voltage is 5 volts, which is greater than VTN, so transistor will be on and input will be passed to the output. Again, input is connected to node D, which is at 5 volts. So as NMOS transistor produces degraded output, so the output at node F will be 5 minus 1 volts, which is equal to 4 volts again. The next node G is connected to the output of NMOS pass transistor. Again, the gate is at 4 volts as we have calculated recently, so it is still greater than VTN, so the transistor will turn on and input will be passed to the output. As input is at 4 volts, And because this is again a logic level 1, so it will again be degraded at the output. By how much? By VTN. So the output will be 4 minus 1 volt, which is 3 volts this time. So this is how you can estimate the voltage at different points in a given circuit based on past transistors. And that's a quick overview of past transistor circuits. I hope this helped you understand how these transistors work in a digital circuit setting and some of design considerations involved. If you enjoyed this video, please give it a thumbs up and subscribe for more tutorials on electronics and circuit design. Feel free to leave any questions in the comment box below and I'll be happy to answer them. Thanks for watching.